All right, guys, we have one more exponential equation. Again, this is just an exponential expression on one side, and so you want to make sure that's alone. It is. There's nothing being added to it and nothing being multiplied by it. Here the base is 2. So when I take the log, I'm going to use base 2. This is log base 2 of 2 to the 4x is equal to log base 2 of 20. This over here simplifies to just 4x. And log base 2 of 20, I don't know what that is. And so I'm just going to leave it. I'm going to leave it log base 2 of 20. I need to still solve for x, so I do that by dividing both sides by 4. I get x is equal to log base 2 of 20 all divided by 4. The whole thing, the log and everything, divided by 4. I don't know what log base 2 of 20 is. You can't divide the 20 and the 4. That's not the way it works. So this whole thing, log base 2 of 20 divided by 4. That's your answer. All right, the next 4 problems are log expressions. So guys, we want to check and make sure our bases are the same. I have a log on both sides. For both of these, my base is 4. So when I make these an exponent, I'm going to use a base of 4. The other thing I want to do is I want to check for extraneous solutions. I want to exclude some solutions before I get too far. So this is x minus 4 in parentheses. That means in order for this to stay positive, x has to be greater than 4. And then this 6 minus x in parentheses, guys, because that's a negative, this is x is less than 6. Because that negative there changes the sign of what's inside the log. So x has to be less than 6. And if x has to be greater than 4 and less than 6, then the way that looks is 4 is less than x is less than 6. This is our domain restriction. So we're looking for a number between 4 and 6 for this problem. Now, I've established that the base is 4. To get the x minus 4 and the 6 minus x out of the parentheses, I have to make them both an exponent on a base of 4. So I write big 4's, one on each side of the equal sign. And what that does is it allows this x minus 4 to come out of this log expression. So this simplifies to just x minus 4, and this side simplifies to 6 minus x. And then we're going to solve for x. So you do that by adding x to both sides. I get 2x minus 4 is equal to 6. Add 4. 2x is equal to 10. Divide by 2. X is equal to 5. And once we get that answer, we want to double check and make sure it fits our domain restriction, and it does. 5 is between 4 and 6, and so we're good. That's our solution. We're good. All right, over here, this natural log of x squared is equal to the natural log of 81. Because you're squaring x, and this is something you have not seen before, and this specifically will not be on the test, but it is interesting to see, and it is interesting to look at. Because we are squaring this number here, it will always be positive. And so the only value, negative 2 squared is positive 4. Negative 5 squared is positive 25. And so I can put negative numbers in here. I can have a solution that's negative. The only thing that's a problem is that we can't take the natural log of 0. And so x can't be 0, and that's our only domain restriction. That's the only restriction on solutions, is that 0 cannot be a solution. Now, these are natural log, which means they have a base of e. And so when I go to make them an exponent, the base I'm going to use is e because it's natural log. And so I write the big E, 1 on each side of the equal sign. And what happens then is that this side simplifies to x squared, and this side simplifies to 81. You can solve for x by taking the square root of both sides. You get x is equal to positive or negative 9. And because the only restriction here is that x cannot be 0, x is equal to 9 and x is equal to negative 9. They both hold up, and we're good. Good. All right, guys, 22. Here we only have a log on one side of the equal sign, so this is approached just a little differently. Now, I do want to look at this and formulate a domain restriction, a restriction on the solutions I can have. So you do that by finding out where the inside of the log would be 0, so 2x minus 5, where would that be 0? That happens at x equals 5/2. Okay, so x must be greater than 5/2. That's our restriction on our solutions. Now, in order to solve this, we have a base of 3. So this is log base 3 of 2x minus 5 is equal to 3. And because my base is 3, that's the base I'm going to use when I make the log and exponent. And remember, we have to do it to both sides. This side simplifies to 2x minus 5. And this is 3 cubed. And we know what 3 cubed is. It's 27. So 2x minus 5 is equal to 27. And then solve for x. And then you need to check and make sure that your solution fits your domain restriction. X is 16 is greater than 5/2. So we're good. All right, last log problem, number 23. I've got 2 logs over here and a number here, and if that happens, you got to put your logs together. And that's only happening because I have 2 logs here and a number here. Okay, if I had like these first 2 problems, that's 1 log on each side, we can work with that. But if you have 2 logs and then a number, you got to put your logs together. Okay, so remember, if we're adding logs, that means you multiply what's inside the log. So we're going to multiply what's inside the log. All right, and then we've got a base here of 3. So when I make that log and exponent, I'm going to do that on a base of 3. So you get x times x plus 8 is equal to 3 squared. And that's x squared plus 8x is equal to 9. This is a quadratic equation, which means you need to set it equal to 0. So I'm going to subtract 9 from both sides. X squared plus 8x minus 9 is equal to 0. And then you factor. And you're looking for things that multiply to -9, but add to positive 8. Multiply to -9, but add to positive 8. And when there's a 1 unit difference between these two, you know, this is 9 and this is 8, you're looking at 1 and 9. So this is x plus 9 and x minus 1. So you got x is equal to -9 and x is equal to 1. Those are our solutions. Now, I did not find my domain restrictions before I started this problem. I just went straight into the problem. But from the log base 3 of x, this one right here, I know that x has to be greater than 0. And from the log base 3 of x plus 8, I know that x has to be greater than -8. And remember, you take the more restrictive of the two, so the one that eliminates more numbers. And in this case, that's the x is greater than 0. It gets rid of all negative numbers. This only gets rid of negative numbers after -8. So I take this one, and I look at my solutions. 1 is fine, but -9 is not. So we cross it out and we write extraneous. All right, guys, 24 and 25 are application problems. Notice that they gave you the formula to use on both of those problems, and notice that the formula is the same for both problems. It's the continuously compounded interest formula. Okay. If you deposit $200 in an account that pays 7% annual interest compounded continuously, how long will it take for the balance to double? So we're using this formula right here, A equals PE to the RT. And in this case, we're depositing $200, so that's my initial amount. And then if I want that amount to double, That's 200 times 2, which is 400. So that's my A value. My rate is 7%, and remember we write that as a decimal, so it's 0.07. And then they're asking us to figure out how much time it's going to take for the balance to double. So we're looking for T. All right, guys, we're going to set this up. So I've got 400 is equal to 200 e to the 0.07 t. And so it's that t we're looking for. We've got to get it out of an exponent, but first we've got to get the e with the exponent alone. So I divide both sides by 200. I get 2 is equal to e to the 0.07 t. And we have a base of e, and that means we use natural log, right? If you've got a base of e, you use natural log. So I'm going to take the natural log of both sides. Ln of 2 is equal to ln of e to the 0.07 t. I don't know what ln of 2 is, so it stays ln of 2. And this simplifies to 0.07 t. And to solve for t, you would divide both sides by 0.07. So t is equal to the natural log of 2 divided by 0.07. And we can do that in the calculator, and when you do, you get a familiar answer, which you should have noticed at this point. It was one of the examples we did yesterday in class, and also was on your homework. All right, so 9.90212 years. All right, 3 decimal places, please, unless we're talking about money. All right, guys, looking at number 25, it says new and rare presidential $2 coin has been projected to appreciate at 33% this year. After how many years will the coin be worth $50? So we are again looking for time. They want us to tell them after how many years will the coin go from being worth $2 to worth $50. So we're looking for T. The amount we pay for the coin, that's our principal amount, that's 2. And the amount the coin's going to be worth at the end is 50. And then our rate of increase, not interest rate, but rate of increase for this is 33%, so it's 0.33. And so, set that all up, right? It's 50 is equal to 2e to the 0.33 t. And again, that looks just like the problem you did up here in 24. The numbers are different, but that's it. So I need to get the e alone. I divide both sides by 2. 25 is equal to e to the 0.33 t. And because it's e, I use natural log. So ln of 25 is equal to ln of e to the 0.33 t. I don't know the natural log of 25, so it's going to stay 25 for now. But this simplifies to 0.33 t. And then divide by 0.33. So we get t is equal to the natural log of 25 divided by 0.33. And we can throw that into a calculator. And when you do, you get 9.75416 years. So 9.75 years after you purchase that gold coin, a rare it's not gold, it's a rare presidential coin for $2, it's going to be worth $50. All right, guys, that's your review.